Hello everyone, welcome to the CS 110 Computer Science Introduction class. My name is Amit Brambhat and I'm your instructor for the course. And today we are going to go over the slides from Chapter 1. So let me real quickly share my screen. Okay, so welcome. In this chapter, we are zooming out to see the big picture of computing. What's inside a computer system, how abstraction helps us manage complexity, how hardware and software evolved, and how the role of users has changed over time. By the end, you will be able to describe the layers of computing system, explain abstraction with real examples, recognize the key milestones in hardware and software industry history, and distinguish between system programmers who build the tools and application programmers who use these tools to solve the problems. We'll also connect these ideas to the big themes in computing that show up everywhere: data, algorithms, programming, and Internet's global impact. Think of today as building the mental map. We'll use this framework throughout the course. Goal of this chapter is to describe layers of computing, concept of abstraction, history of computer hardware, changing role of computer user, and the big ideas as we just discussed. So computing systems are dynamic. They constantly evolve in capability, scale, and how we interact with them. And at a high level, computing system combines hardware and software, tangible components, the instructions that tell us hardware what to do. What's crucial is the interaction between the two. Software turns human intent into precise commands, and hardware executes those commands faithfully. This interplay is what enables everything from your phone camera to cloud scale AI. As we move forward, we'll keep asking, how do these layers cooperate and what abstractions make that cooperations manageable? So as we just discussed, hardware is the wires, printers, circuit boards, keyboards, etc., and software is the instructions that we provide to these hardware. Chips, memory storage, they are also hardware. Just think of what all different hardware you use to interact with softwares. These may include your Bluetooth headsets or microphone or any of the systems that you use while interacting with computing systems. So as we see in the next slide, these are the layers of computing systems. The topmost layer is communications, and then we go down to applications, operating systems, programming hardware, and the bottommost component is information. So it's a layered to manage complexity. And from the bottom up, we can see the hardware is what we see, and the firmware, which is made of, which is a part of operating system, and then system libraries, language runtimes, and finally applications at the top that are made out of usage of different capabilities of these uh, systems. Each layer provides service to the layer above while hiding the intricate details below. This is a sense of modular design. An app doesn't manually move bytes on the disk, it asks the OS to save a file. The OS in turn relies on drivers and ultimately the hardware controls does the low level work. This layered view is powerful. It enables specialization, portability, and rapid innovation without having to redesign everything at once. Abstraction is a mental model that removes complex details. This is the key concept. Abstractions, we'll talk about those throughout the text in upcoming slides. It's the single most important concept in computing. It's a mental model that hides unnecessary details so we can focus on the right level of problem solving. You use it every day, files and folders instead of raw disk blocks, variables instead of registers, high-level languages instead of machine code, and APIs instead of device specifics. Good abstractions are simple, consistent, and predictable. They reduce cognitive load, prevent errors, and allow teams to collaborate at different levels. Keep asking yourself as we go, what details are hidden, what guarantees does the abstraction provide, and what performance or flexibility trade-offs does it imply? So here is an example of internal and abstract view where you don't see your car engine operating or how it works while you are driving the car. You basically focus on the steering, the gears, if your car has any, maybe the audio systems, and most importantly, the pedals that we press when we make the car go or stop. And it democratizes its capability. You don't need to be a chip design engineer to build an app. You don't, just like you don't need to be a mechanic to drive. Still, knowing a bit about what's under the hood helps you debug issues as and make better design choices. History of early computing. Early computing is focused on mechanizing calculation. The abacus provided framework for representing numbers. In the 1600s, Blaise Pascal built a mechanical calculator that performed basic arithmetic. In the 1800s, Joseph Jacquard introduced punch cards to control looms, an early example of programmability through encoded instructions. Charles Babbage conceptualized an analytical engine, a general-purpose programmable machine with a control unit and memory, anticipating many modern computing ideas. These milestones planted the seeds for programmable general-purpose computing. Ada Lovelace was the first programmer. She described algorithms for Babbage's engine and introduced the concept of loops. Alan Turing formalized computation with the Turing machine and pioneered ideas in AI. Then came large electromechanical and electronic machines such as Howard Mark I, ENIAC, and UNIVAC 1. Huge systems that transformed mathematics, physics, engineering, and economics. The pattern you'll see again and again. New hardware capabilities enable new software paradigms, which in turn expand what problems we can practically solve. The first generation computers used to be vacuum tubes, bulky, power-hungry, and heat-intensive. Storage was provided by magnetic drums, a memory device that rotated under a read-write head. Punch cards evolved into magnetic tape for sequential storage. Programming was physically and temporally constrained. Access times depended on where data sat on drum or on tape. Despite limitations, this era proved digital electronic computing was viable and set the stage for rapid progress. Transistors replaced the vacuum tube, fast and small, durable and cheap. Magnetic cores replaced the magnetic drums, information available instantly, and magnetic disks replaced magnetic tape. Data can be accessed directly. It also reduced size and cost, making computers more, accessible to organizations beyond governments and large labs. Third generation hardware from 65 to 71. The big breakthrough we had here were integrated circuits, placing many transistors on a single chip that made machines smaller and cheaper, faster and more reliable. Terminals with keyboards and screens improved interactivity. You can think of this as beginning of the modern system architecture. Enough performance density to run more sophisticated operating systems and languages, and enough interactivity to support the time sharing and multi-user workflows. The fourth generation hardware came from 71 onwards. With large-scale integration and microprocessors, we saw the rise of personal computers and workstations, and the birth of companies like Apple, Sun, Dell, etc. Over the time, laptops and tablets, smartphones gave everyone a portable computer. In parallel, networking matured from Ethernet connected PCs and file servers to LANs, and eventually the Internet. Today, we also have parallel computing, multiple cores, and distributed systems, unlocking massive performance data and AI workloads. Parallel computing and networking. As we talk about ARPANET and LANs in Internet. The first generation software. Early software meant machine learning language, binary instructions, and later assembly language with mnemonic codes translated into machine code. Programming roles diverged into systems programmers who built the core tools and application, programmers who used them to solve domain problems. It was close to the metal powerful but error prone. The need for productivity and portability set the stage for higher level languages. Second generation software, high level languages emerged like Fortran, COBOL, and Lisp, bringing English like syntax that dramatically improved programmer productivity. Compilers and translated this code down to machine instructions. This layer is prime example of abstraction. Developers think in terms of algorithms and data structures rather than registers and opcodes, enabling broader participation and faster development. Third generation software from 65 to 71. We saw robust system software, operating systems that schedule programs and many resources, language translators, and utilities. There is a clear separation between users and hardware, allowing programmers to build software for generalized audiences. This era makes computing more service oriented. The OS provides standardized capabilities and applications target those services instead of bespoke hardware behaviors. Third generation software, as we say, saw the machine languages at the bottom, and then assembly language, high languages, system software, and on the top we have application packages. Fourth generation software, from 71 onwards, we had structured programming, languages like Pascal and C++, formalized program design and controlling structures, improved correctness and maintainability. At the same time, end user applications exploded, spreadsheets, word processors, and database systems, bringing computing power to business users, analysts, and creators. The story here is accessibility, tools that let non programmers achieve sophisticated results. Fifth generation software, 1990s to present. Modern software emphasizes object-oriented design, pervasive networking, and the World Wide Web. Windows and other platforms standardize user experience and development ecosystems. Java and similar languages popularized portable object-based development. Most importantly, the web enabled global communication and distribution. Today's user can be highly productive with almost no computing background, proof of how far abstraction and tooling have come. Computing as a tool, the roles. Think of two broad roles. System programmers build system tools, operating systems, compilers, and frameworks. Application programmers use those tools to deliver solutions. There are also domain specific programs that encode expertise for particular fields: finance, healthcare, graphics, AI. Understanding where your work sits in this ecosystem helps you choose the right abstractions and collaborate effectively across specialities. Computing as a discipline? A classic question: what can be efficiently automated? Answering that demands four skills: algorithmic thinking, designing step by step solutions, representation, which means choosing the right data models, programming, expressing solutions precisely, and design, which is structuring systems that scale and evolve. Mastery across the skills lets you reason from theory to implementation to user value. What do you think? Computing as a discipline, is computer science a mathematical, scientific, or engineering discipline? Well, it's a blend. It uses mathematical rigor for proofs and complexity, scientific method for experimentation and evaluation, and engineering for building reliable systems under constraints. That hybridity is a strength. It encourages both theoretical elegance and practical impact. Systems areas. Example of system areas include algorithms and data structures, programming languages, architecture, operating systems, software engineering, and human-computer interaction. These domains define capabilities and constraints the rest of the computing world builds upon. If you enjoy building performance platforms, optimizing performance, or designing developer and user experiences, systems might be your home. Application areas. Application areas apply computing to real-world domains, numerical systems and symbolic computation, databases and information retrieval, intelligent systems, graphics and visual computing, net-centric computing, and computational science. These are where users feel impact, discovering drugs, rendering films, answering questions, or modeling climate. The best work often happens at the intersection of systems and applications. Big ideas for computing. The big ideas cut across everything: creativity, abstraction. Creativity is inventing new solutions and managing complexity using abstraction. Then representation and meaning from data and information. Then procedures and efficiency using algorithms. Precision and expression using programming. Communications and scale using the internet. Ethics, economics, and society, which is the global impact. You have to keep these themes in mind. They are the lenses that clarify computing problems that you face. What disparity does the term digital divide describe? Is the gap between those with reliable access to technology and those without. What's an E-rate program? E-rate subsidizes internet access for schools and libraries, while one laptop a child is aimed to expand access to learners worldwide. Developing nations face additional challenges: infrastructure, affordability, and local language content. As technologists, we influence who benefits from this technology. Equity and accessibility should be design requirements and not afterthoughts. Ada Lovelace. She's often celebrated as the first programmer, articulating how a general purpose machine could manipulate symbols beyond arithmetic and describing loops. These stories matter because they remind us that computing is a human behavior, human endeavor, vision, creativity, and collaborations are essential as circuits and codes. Who said analytical engine weaves algebraic patterns? Well, that was Ada Lovelace. Where was the first nanotube computer built? At Apple. What companies turned Jobs and Wozniak away early on? And what computer company was launched in a garage? I guess these are the questions you should ponder on and look up yourself. Where is the Computer History Museum? What is Room to Read? It's a nonprofit advancing literacy and gender equality. When and where the first CS department was formed? Purdue and Stanford in the 60s. I'm going to end the part one of this video now and see you in part two.